Okay, so last time we left off with looking at systems of linear equations, right? So refreshing your memory a little bit on that. A system of linear equations is when they give you more than one equation, usually just two. We don't want to get too crazy here, but it could be more than two, 3, 4, 5. It could get really nasty, but we really just stick to the two most of the time. So let's just say two. Two equations are given, and because in this chapter we're focusing on lines, these are linear equations. Okay, so two linear equations are given, and that's the system, right? Both of them together. A solution to the system is when we find an ordered pair that is a solution to both equations at the same time. We found it by the graphing method yesterday. So for instance, we saw this guy. Here's the system. Y equals to 2x plus 4 is one linear equation, and y equals to negative x plus 1 is another linear equation. And we graphed them both. We got this guy. We got that on our calculators, right? So it gave us that line and that other line. So we saw from our calculators that the two intersect at the point negative 1, comma 2. Now keep in mind that the lines, the blue line and the red line, sometimes it's useful to think of them as just a bunch of ordered pairs, a bunch of dots. There's so many ordered pairs, in fact, that it looks like a solid line, but really it's just an infinite number of dots, where every dot is an ordered pair of an x comma y that makes that equation true, right? So there's just so many of them, it just looks like a solid line, but it's really an infinite number of ordered pairs. That's another way to think about it. And so one particular ordered pair is the value negative 1, comma 2 that happens to be a solution to both. So for instance, we had the equation y equals to 2x plus 4 and y equals to negative x plus 1. Here was our system, and from the graph we were able to figure out that the solution was the point negative 1, comma 2, right? And what it means for it to be a solution is that if I replace the x and y with this x and y, I will get a true statement there, and I will also get a true statement here. That's what it means for it to be a solution. So the solution is this, and I'll say because if we replace the y with a 2, so 2 is the answer when we multiply 2 times negative 1 plus 4, right? So this is the x and the y. Here's the x and the y. I plugged in x equal to negative 1, the y equal to 2, and so I get this, and of course 2 does equal to negative 2 plus 4. Negative 2 plus 4 is 2. This is a true statement. Good. And also, so that comes from there, and then the other one leads to the idea that 2 does equal to negative 1 plus 1, right? So here I have a negative already, negative times x, and x happens to be a negative 1. So we end up with negative times a negative, or positive 1. Positive 1 plus 1 is 2. Both of these are true. We did find the answer. True and true. Good? Questions, comments, issues? No. Okay, so we're going to continue the same idea in this section. We're going to be given a system of equations, and we're looking for the answer, such as this one. So we solved it by the graphing method, but now we got to learn two other methods. One is called the substitution method, and the other one's called the elimination method. Okay, so the first thing I'm going to do is I'm going to solve this exact same question by using the substitution method. And the benefit here is that we already know the answer, so it'll be easier to kind of get an overview of what we're doing as we're solving it. And then afterwards we'll solve a new one where we won't know the answer, and then things will work out. Okay, so just a rough sketch of the graph for this thing was this. There was some equation that way and some equation this way, right? This one was the y equals to 2x plus 4, and this one was the y equals to negative x plus 1. And we saw that at this point where they crossed, this was the value negative 1, and over there this was the value 2. So therefore right there was the ordered pair negative 1, comma 2. So that was sort of the graphical solution to this one that we used our calculators. Good? Good? Okay, so let's start over again. Let's pretend we don't know the answer, but we sort of do anyway. So we're still solving this. You know, solve this same thing. Y equals to 2x plus 4 and y equals to negative x plus 1. Okay, so I'm going to go back to this graph. So we're looking for these two things right in here, right? So what I'm going to do is I'm going to kind of sketch the same thing. And again, I'm cheating a little bit because I already know what it's supposed to look like. I know that they cross in quadrant 2. So in this example, granted, I'm kind of cheating a little bit. But we'll see how it works, and then we'll do it with one where we don't know the answer. So I know that right here is the input that makes it work out, the solution, and that's the output. But and I know that this really is a negative 1, but I'm going to pretend I don't know what it is, and I'm just going to call it A. And I don't know what this is, but I'm going to call it B. I already know. I already know that the solution is negative 1 comma 2. So I already know that this really should be the negative 1 and this should be the 2, right? In the sketch of the graph. But we're trying to figure out that answer. So we're going to pretend we don't know. So the solution, we're going to say the solution is A comma B. We're gonna assume there it is. It's A comma B, that's the answer. So if that's in fact the solution, as we saw before, you know, this was negative 1, 2, then that must mean that if I replace the x and y with those specific values, I'll get a true statement there and a true statement there. That's what it means for it to be a solution. So from the first one, I'll get that the b is equal to 2 times the a plus 4. And from this one, I'll get that the b is equal to negative a, so negative a plus 1. Is that okay? Questions, 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 questions? Okay, so now it's a very subtle distinction, because really all I did is I changed the x's for a's and the y's for b's. But there's a very subtle and important distinction here. Up here, this represents any input and any output pair. Right? This is describing a relationship, a situation where you give me an input, I'm going to double it, add 4, that's the output. Here we have a situation where I'm going to multiply the input by negative 1 and add 1 to it, that's the output. But this x and this x are not always the same value. They don't represent the same value always. Whatever input you give me, I can put it in there and get the resulting y. So even though they're the same letter, they're not really the same value always. They can be, but they don't have to be. Whereas over here, these are the same values. This isn't representing any input. This is the special input that's the solution. Right? That's this number. I already know it's negative 1, but we're trying to discover that. But this A is the negative 1, and this B is the positive 2. It's not any input-output pair. It's the special input-output pair that is a solution to the system. Right? So it's a very subtle, yet very important distinction. Any questions about that? No? So this is just input-output pairs, whereas this is the special input-output pair that is a solution to the system. So what's special about that? Well, since they represent specific numbers, they're the same value. This is negative 1. We're just trying to discover that for ourselves, but we already know the answer is negative 1 there, and this is a 2. Right? We saw that from over here. This equation is the same as this one. Right? This is the A, this is the B. We're just trying to discover that that's the A and that's the B. Right? Good? Okay, so the benefit then is, since this is a 2, we already know that, then they both equal a 2, therefore they could be equal to each other. Right? In other words, from the other page, since we know the answer is, let's say A equals to negative 1 and B equals to 2, then this is really 2 equals to 2 times negative 1 plus 4, and this is really equal to 2 equals to negative times negative 1 plus 1. right? So again, this is cheating since I already know the answer is that. So because I know the answer is that, I know that this and this are the same thing, right? This is the A, this is the B. Okay, so because they represent the same quantity, then I can substitute one into the other. In other words, I'm going to take this thing right here, and it's going to be B equals to negative A plus 1. But then on this side, instead of this B is equal to that. So I'm going to use that and substitute this B with that. So I'll end up with 2A plus 4 equals to negative A plus 1. Good? Any questions? Any questions? Let's see if... I'll put them in different colors so it's maybe a little clearer. So I'm saying that here, this is this B in orange, which is this B, right? I just copied it. But then I said, well, look, this right here, this B right here, this green one, is the same as that, and it happens to be equal to this. So I'm going to take that and substitute it right in there, and that's why I set this B equal to that from there. Okay, so I just said, well, they're both equal to B. All right, over here, they both equal 2, so I could have said that this equals that, because they both equal 2. Same thing over here. They both equal B, which we will discover in a minute that B is really a 2, but it's just B, so they equal each other. So I set them equal to each other, I substitute this B for that, and now the benefit is that I have a new equation that only has A's in it. I was able to get rid of the B's. There's only A's in it, therefore I can solve for it. I couldn't really solve for it before because there were two different kinds of letters, so I really couldn't get like a numerical answer. But now there's only one kind of variable in A, so now I can solve for A and I'll figure out that A really is negative 1. Okay, so solving for A, I'm going to move this over, plus A, I end up with 3A plus 4, these guys cancel, I get 1. I end up with 3A plus 4 equals to 1, so move this over, minus 4, I get 3A equals to negative 3, so therefore A equals to negative 1. Got it. Good? Questions? Yeah? So I was able to figure out for myself that the A really is a negative 1. Now I just got to find the B. Well, that should be easy. Now I can go back and use either one of these equations, substitute the A for the discovered value of A equals to negative 1, and now I can solve for B. It doesn't matter which one you choose. So let's just choose the first one. So let's say we use B equals to 2A plus 4, but now we know that the B is really, the A is equal to negative 1, so this is 2 times negative 1 plus 4, and so B equals to positive 2. So we have our answers. We were able to get it on our own. Any questions? Sort of, kind of, think about it? No? Nothing? No? Okay, I know what you're thinking, well, I kind of already knew the answer, so maybe was I kind of cheating too much? I kind of was guiding you toward the answer. So let's look at one where we don't know the answer. We'll follow this process along, and hopefully we'll be able to get to the right answer, and then we can confirm it. Right? How can we tell that we got the right answer? Well, this would be what we would do. We would go back to our original equations, replace the x and y with what we think is the answer, and if it works out, we should get a true statement there and a true statement there. Right, to solve the system of equations. Good? Questions? All right, so now we don't really know the answer, so we really can't cheat too much. We have y equals to x minus 1, and we have 3x plus 2y equals to 13. Here's my system. Guys, can we stop the side conversation? So there's our system right there, right? We're trying to find that answer right in there. From yesterday, if you recall, we know that if we're graphing two lines, there's only one of three things that can happen. When we graph two lines, either they form a nice sort of X at some point, therefore there is one unique answer where they cross, or maybe we graph the two lines and they form like parallel lines, they never cross, there's no solutions ever. Or the third thing that can happen is this really weird thing where we draw the first line and we go do our work and it turns out that the other line is exactly the same one, So they kind of like touch everywhere, right? They're the exact same line. So this is called consistent, inconsistent, and dependent. Okay, these two are kind of weird sort of cases, right? There's no solution, there's an infinite solution. This is the case we want to focus on. So whenever you're approaching these questions, we assume that this is the case. There is a unique answer, one unique answer that where these cross, and if it turns out you were wrong, that it was one of those, then the algebra will guide you to that. You'll see something weird happens, and that's how we know that our assumption was wrong. Okay, so we always assume that there is a that it's a consistent system with one solution, where this is some sort of A and B, where the ordered pair that's a solution is some integer value. Not integer value, some sort of ordered pair solution. Okay, so that's the first thing we're going to do here. We're going to assume it's true that this is consistent and that it has a solution A comma B. Right? Assume the system is consistent and the solution is A comma B. Some special choice of X and some special value of Y is the ordered pair that's a solution of both of these. Okay? So that means that when we do that at this solution point, at the solution point of A comma B, then it must be true that B is equal to A minus 1. And it must be true that 3A plus 2B is equal to 13. Right? What did I do? I just took this guy right here and I replaced the X and the Y with A and B. And I took this guy right here and I replaced the X and Y with A and B right there. A very subtle little distinction that I think conceptually makes a big difference. However, it's not very popular in most books, so I'm not sure about this book. I'm not sure if they bothered doing this. There is a slightly faster notation. I don't know if faster is better, but there is a slightly faster. So we'll do it this way with the A and B thing for a little bit, and then we'll see what most people do, which is a slightly faster way of doing it without doing the replacement, but the same conceptual idea, is at work. Yeah, question?
So on the test, when we take 3 and 4, we need to switch it to A and B?
Nope, it's up to you. If it makes sense to you, if you need it for the problem to make sense, then you should do it. I would recommend it at least a few times at first, but it's up to you. If you like the shortcut better and you understand why it works that way, then that's fine too. Okay, so we're saying at this point. So a very subtle distinction here. These aren't necessarily the same x's. This is any input-output pair, right? Any input-output pair is being described here. Whereas here, we're not saying it's any input-output pair. It's the unique input-output pair that's a solution to both. And that's important because that must mean that this is the exact same value as that one. Always. It's the same number. We don't know what that number is, but it's the same number. Maybe they're both 7 or they're both 13. I don't know. We're going to discover what that is. But same thing over here. This A and this A are not any inputs. They're the same input. They're the special input that gives you this special output. Okay? So because that's the case, because this and this represent the exact same number, I get to rewrite this B this way. And that's where the substitution part comes in. Okay, so I'm going to take this guy, I'm going to rewrite it as 3A plus 2B equals to 13, and I'm going to recognize that, well, this B right here, this B is the same as that B, so I can rewrite it as A minus 1 instead of B. B equals to A minus 1, so I'm going to rewrite it right here as A minus 1. And then everything else stays the same. 2 there, 3A equals to 13. Good? Questions, questions, questions? All I did so far is replace that B right there with this one. So I took this equation, replaced the B in there with that equation, and now I have a new equation that only has A's in it. That'll make it easy to solve. That's the substitution part right there. I said, look, the b's are the same, therefore I can just plug them in there. Good? So now we solve for a. We distribute, combine like terms, we end up with 3a plus 2a minus 2 equals to 13. Then that means that 5a minus 2 equals to 13, which means that 5a equals to 15, which means that a equals to 3. Okay, so now we have half our answer. I know this guy has to be a 3. Okay, it can't be a 5, it can't be a 7, it's a 3. And it's a 3 there, and it's a 3 over here as well. It's the same a. So only one value here, only one input value, which is 3, which is the solution, right? In the solution to the system, the input that works is a 3. Got it? Good, good, good. So we're halfway there. Now we just got to figure out what the b is. In order to find the b, well, you can go back to any one of these equations, either one of these equations, and solve for it. Well, this one's easier, right? b equals to a minus 1, and we already know what the value of a is. So that makes it easy. I can just substitute a into there. I get b equals to a minus 1, and I just discovered the a is a 3. So b equals to 3 minus 1, or b equals to 2. So I have my solution pair. My solution pair is right here. b equals to 2, a equals to 3. When we write our solution, remember the order does matter. The a is the input, it's the x, and the b is the output, it's the y. So I have to rewrite them in that order. So my solution to the system of equations is the ordered pair 3, 2. Good? Questions, comments, issues? No? 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 We can check it. To check it, we'd have to go back to the original equations over here. Let's make some room here. To check it, that means that if I replace the x and the y with this ordered pair, I should get two true statements. Is it true that 2 equals to 3 minus 1? Yeah, right? This is the x, this is the y. So if I replace x equal to 3, y equal to 2, I get that. That's true. What about over here? If I rewrite this as 3 times 3 plus 2 times 2, does that equal to 13? 9 plus 4 is 13. Yep, it worked out. This is the ordered pair. Good? We can also double check it by graphing them. If I graph this equation, I graph that equation, I know they're going to form an x, and I know that the place where they cross is at the point 3, 2. Good? Any questions? Questions? No? Sort of? Kind of? Sort of? Kind of? Okay, let's solve this exact same thing without doing the a part of it, the substitution part of it. You don't have to do that. I think it makes it easy to see conceptually what we're doing. So we have y equals to x minus 1 and 3x plus 2y equals to 13. Okay, so I like thinking about the fact that at the point where they cross, we have a unique choice of x and y such that they are the ordered pairs. I like thinking about that, but a lot of books don't really bother with that. So they just jump into the substitution part of it. So that part, we could say, we can do it this way. That would be 3x plus 2y equals to 13. And then we can go, oh look, that y right there is this y right there, and they substituted there. So they end up with 3x plus 2 times x minus 1 equals to 13. Okay? Now, even though they didn't write it down, the reason you do that, you have to kind of know why this is allowed. And so maybe in your head you're thinking, at the point where they cross, the x and the y are the same. Just at that point. Right? That's the whole point of them being a system of equations. I bothered to go through the process of calling them a and b, but you don't have to. So at the point of intersection, this y is the exact same as that y. That's why they substitute it this way. Now they have a new equation that just has x's and y's. Okay, well then you just solve for x here. 3x plus 2x minus 2 equals to 13. Right, move that over, bring this over. 5x equals to 15, x equals to 3. Same thing as before. So they just don't, many books just don't bother with the substitution of letting x equal to a and y equal to b. That's all, right? So now once you solve for the x, then you can just go back to the original and solve for y. Y equals to x minus 1. So y equals to 3 minus 1. Y equals to 2. And so you get the order pair 3 comma 2. Any questions? No? No? Who likes this better than doing the a and b substitution part of it? Okay. So do you like it better because, so it's often the case I get that people like it better. I like it better in the sense that it's a little bit faster. But I think it's important to at least see it the other way at least once so that you understand this better. But you're not required to do that. So on the test, if you want to do it this way, sort of the quick and dirty way, I will assume you understand why you're allowed to do that, and I hope that you keep that in mind, because as things get more and more complicated, it'll be important to keep that in mind. If this system is really nasty, 2 equations, 3 equations, 4 equations, more variables, weird things happening, it might be better, down the road, you might have to go back to the idea of this, right? Like there is some solution A and B, let's plug it in and let's find those specific values. Sometimes you'll find that that might be better, right? Especially if there's lots of solutions. For instance, what if we're working with something that has lots of wigglies on it? It goes this way, that way, this way, that way, and then there's maybe a line. It crosses at lots of places. So there might be lots of solutions, and it might be a little bit easier to start calling them the A-B solution, the L-K solution, the P-Q solution, I don't know. Or you can, come up with some other notation. But in some cases, it might be better to do the step of rewriting them by some other variable. But it's up to you. Hopefully it makes sense. Any questions? No? Okay. So this is the substitution method. So we found the answer to be equal to 3 comma 2. And so, let's go back to this thing. So if we used our calculators, right, we go to our calculator, we graph it, we would get this. Okay, so we have the line this way. The red one is the line negative 3 over 2x plus 13 over 2. That would be this if you solve for y. If you move this over, divide everything by 2, you would end up with negative 3 over 2 as the slope, plus 13 over 2 as the y-intercept. And then here's the other one, the blue one is this one, slope of 1, y-intercept of 0 comma negative 1. So as you can see, it crosses in quadrant 1. We can see the solution, and we can use our calculator to find the intersection, and we see that the intersection is 3 comma 2. Good? Questions, comments, issues? All right, so in general, describing what happened, how did we solve it? Okay, you're going to be given a system of equations, right? Right now we're dealing with linear equations. Right now we're only dealing with 2 equations. So 2 linear equations are going to be given to you. First of all, we have to isolate one of the variables in one of the equations if that hasn't given to you. So here we were lucky that this equation had already been solved for y. That's okay. If it's not solved for y, then you're going to have to solve for one of the letters. It doesn't have to be y, whichever is easiest. Then you're going to substitute that letter into the other equation. You got to make sure you use the other equation. That'll give you a new equation that only has one kind of letter into it. So like that's when we substituted this, we substituted that. So we get one equation that only has one kind of letter in it. Then we solve for that letter, that we solve the value of that variable. Then we go back and plug that value into one of the original ones to get the other variable, and then we're done. Okay? Good. All right, so let's do one more like this. This one. Okay, so now we have x minus 3y equals to 4 and 2x minus 5y equals to 5. So we could go through the trouble of this thinking. The answer is sum AB. Let's find the A and B, which means we'd replace the x and the y with A and B for both the systems of equations. You could do that. I think it's still beneficial for some of you guys to kind of think about that. If not, then you can go straight into the x and y notation and solve it that way. Okay? So I'm going to assume assume the system is consistent. With a solution A comma B. Okay? Assume the system is consistent, it's going to form some sort of X somewhere. So if I graph it, one line will go this way, the other line will go that way, something. And there is some place where the answer is A comma B. I have no idea what that is. I don't even know what quadrant it's in or anything. Maybe it's in quadrant 4, maybe it's in quadrant 2, I don't know. I'm just giving you a visual of what that is, some answer. Which means that at that point, where this is a solution, that means that this is going to be the statement A minus 3B equals to 4, and this is going to be the statement 2A minus 5B equals to 5. So we get that. Guys, keep down. So this is the statements that we get from that. Okay, so now we need to figure out a way to substitute. So the steps are solve for one of the letters in one of the equations. Now, which equation and which letter would be easier to solve for? This equation and this equation and which letter? Top equation or bottom equation and which letter? Top one, 4A. It's the easiest one, right? Why not go with the easiest path? Unless you like making life hard, let's go with that one. So we're going to take this one and we're going to solve for A. So we're going to say A equals to 4 plus 3B. Good? I solved for one of the letters in one of the equations. Now I'm going to go with the other equation, which is equal to 2A minus 5B equal to 5. And this is where I'm going to do my substitution. A is equal to this right here. This is A, and A is right here. So I'm just going to replace this A with this, which was 4 plus 3B. Okay, now that's just the A part of it, which means I still have to multiply it by 2 and subtract it by 5B. That equals to 5. There's my new equation that only involves one kind of letter, the A. Okay, then I'm going to distribute, combine like terms, simplify as best I can. It only has B's in it. So I'm going to distribute, combine like terms, and solve for the value of B. Okay, so if I distribute, I get 8 plus 6B minus 5B equals to 5. So moving this over and solving, I end up with B from here. 6B minus 5B is just going to be B equals, and then if I subtract 8 from both sides, I end up with negative 3. So B equals to negative 3 is my answer. Good. And once I have the value of B, I can go back and use either of the original equations and my newfound value of B, or I could use this equation since I did solve for A this way. A equals to 4 plus 3B. So I'm just going to go ahead and use that guy right there. So A equals to 4 plus 3 times B, and B we discovered was negative 3. So A equals to 4 plus negative 9, or A equals to negative 5. Good? Questions? 4 plus 3B. Okay, so now we got to check our answer. We could have very easily made a mistake somewhere. So we got to check it. So to check it, we go back to our original equations and verify that this special choice of x and y, right, our solution is negative 5 comma negative 3. So let's check if that works out. If it works out, it must be true that we get true statements from both of these. So is it true that negative 5 minus 3 times negative 3 does equal to 4? Let's see, that's going to be negative 5 plus 9. That is equal to 4. And over here we get 2 times negative 5 minus 5 times negative 5 equals to 5. Is that true? That's going to be negative 10. Oh, what did I mess up? Oh, the other way around. Sorry, this is negative 3. Thank you. So this is going to be positive 15. So this will be negative 10 plus 15 does equal 5. True. So it does work out. We found the solution. Good? Good, good, good. Okay, and again, this was utilizing the A and B thing, but you don't have to. If you didn't bother to go through this process of replacing the X and the Y with A and B, then you would still do the same thing, but just using A's and B's. I'm sorry, just sticking to the A and B, X and Y. Okay, so if you didn't go through the process of replacing the X and Y with A and B through this, you just stuck with the X and Y, then it would look like this, right? You'd solve for X, we get X equals to 3Y plus 4, and then you go back to the other equation, and you replace the X with 3Y plus 4, distribute, combine like terms, solve for Y, we get Y equals to negative 3. And then you go back to one of the two equations and you solve for A. You will also figure out that that the X is equal to negative 5. Good? Questions, comments, issues? No? 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 Okay, so that's the substitution method. There's one other method that we're going to look at that's called the elimination method. The elimination method requires us to use two ideas we've already used before at the same time. So let me just refresh your memory on a couple ideas from the previous algebra class, I guess, that you've already used before. So one of the ideas is about equivalent equations. So for instance, if I had 5 equals to 4 plus 1, that's true, right? 5 does equal to 4 plus 1. What if I didn't know those values though? They were just random numbers. I could just say B equals to A plus, I don't know, plus, let's go with E. Right? Something like this. It's just this. Okay, so in this case, what I could do is I could multiply everything by 2. By 2. I can multiply the left-hand side by 2, I would get to 10. Multiply the right-hand side, multiply everybody by 2, I get to 8 plus 2. That's also true, right? It was true before, I multiplied everything by 2, it must be true. Same idea when you don't know the actual numerical values. I could multiply by 5. Well, that means that 5b is equal to 5a plus 5e. This was true, then therefore this must be true, right? If we know this is true, then we know this is also true. Does that make sense? Yes? It was true here, it's true there. So as long as you do the same operation to both sides of the equal sign, you get a new equation that's equivalent to the previous equation. Good? Good, good, good? Okay, well what if we just had like a linear equation instead of this thing? So let's say I had y equals to 2x plus 1, and I decided to multiply everybody by 3. Multiply by 3. Okay, so I'll get a new equivalent equation, 3y equals to 6x plus 3. If this is a true statement, then that must be a true statement. Part of saying it's an equivalent equation means that the ordered pair solutions there are also the exact same ordered pair solutions there. Whatever works there, works here, because these two are equivalent. For instance, what is one ordered pair that works here other than 0? How about if we let x equal to 3, what's the resulting y? Put a 3 there, we get a 7. Right? So 3 comma 7 is a solution to this. It makes it a true statement, right? Which means automatically that 3 comma 7 is going to also be a statement to this one. It's going to be a solution to this one. So let's check it. This is saying that 3 times 7 is going to be equal to 6 times 3 plus 3. Is that true? 21, 18 plus 3, 21. Also true, right? Any solution to this one is also a solution to this one. Why does that matter? Well, what we're going to do in this section is sometimes we're asked to solve this thing, and for reasons that we will understand in a little bit, we decide, nah, I don't want to solve that one. I want to solve this one. This one might be easier. And when you solve this one, you're really solving that one. Got it? Okay, so sometimes we can find an equivalent equation that turns out to be easier, and we'll see why it's easier in a little bit. But as long as you're solving the equivalent equation, you're solving the original one too. Okay, so that's one important idea. We can get equivalent equations by doing the same thing to both sides, like multiplying or adding to both sides. And when you solve the equivalent equation, you're really solving the original one as well. That's why they're equivalents. Good? Okay, so the other idea we got to keep in mind is that, again, we can add or subtract anything we want to an equation and keep the equality of the equation as long as we do the same thing to both sides. So again, if we had like 5 equals to 4 plus 1, if I wanted to, I could decide to add 16 to this side, add 16 to this side, right? And I would get a true statement, right? Of course I could add it, but I'm just going to write it this way. 16 equals to 4 plus 1 plus 16. So of course 21 equals to 21. Yeah, true. I could add 16 to both sides, right? But here's the interesting part. I could add 16 to one side, or I could add something equal to 16 on the other side. So for example, I could add 4 squared. We know that 4 squared is 16, right? So notation-wise, I could leave this as a 16 on one side, and on the other side say plus 4 squared. Right? It should give me the same answer. So I could add the same thing to both sides, or I could add two things that look different but are actually equal to each other. Right? That's because we know that 16 equals to 4 squared. Right? So keeping that in mind, if we know, there's no question, we know that some letter A is equal to 5, for instance, we know that. A is 5. Then I could choose, if I wanted to add A to this side and 5 to that side, because they're equal to each other. Right? So notation-wise, I could say, this side is going to turn out to be 5 plus A, and this side is 4 plus 1 plus 5. Right? Because I added the same thing to both sides. They're both 5. Good? Good, good? Okay. With those two ideas in mind, then we can tackle what it means to do the elimination method. So let's say we have this. Solve this system. 4x minus 5y equals to 3, and 3x plus 5y equals to 11. Here is my system. I want to solve that. Okay, well, the first thing I'm going to do is I'm going to take this top one here, go off to the side. I'm going to rewrite it as 4x minus 5y equals to 3. And I'm going to remind you that I can do whatever I want to both sides as long as I do the same thing. And I can add any value that looks different but is actually equal to each other. So I could, if I wanted to, decide I'm going to add 16 to this side. I'm going to add 4 squared to that side. I could do that because 4 squared is 16. Same thing, right? I could decide, you know what, I'm going to add 11 to this side. And I'm going to add, I don't know, square root of 121. That's 11. Add 11 there, add 11 there. Right? They're the same thing. Okay, well here's the kicker. We are told from the original system that 11 is equal to this over here. This is not to be questioned. We know this is true. They told us it's true. So on that side, I'm going to add 11. On this side, I'm going to add this little statement. 3x plus 5y. Right? So I'm adding 11 to that side. And to this side, I'm going to add this thing. I'm going to add 3x plus 5y. Okay, so what does that look like? Now I bring it all together. I end up with 4x minus 5y plus 3x plus 5y equals to 14. Good? And I should get an equal statement. This should be a true statement because all I did is I added the same thing to both sides. And where's the benefit? The y's. When I add them together, these are like terms. I have a minus 5y, a plus 5y. Oh, they add up to 0. They cancel. That's the benefit here. Okay, and then what I have left, I have 4x and 3x, so that gives me 7x equals to 14. Divide both sides by 7, I get x equals to 14 divided by 7, or x equals to 2. Okay? Take a second, absorb it. Deep breaths. What do you think? Questions, 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 questions? No? 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 Okay, so now that we have the x equals to 2, we have some options. Options are good in life. We could go back to one of these two equations, replace the x with a known value there, and then that'll help you solve for the other unknown. That'll be a new equation that only has one unknown, the y, and then you can solve it that way. Or we can redo the substitution method one more time, which is what I'm going to do just for the sake of practicing it, and for introducing the other idea. Because see here, we just kind of got a little lucky that the y's canceled off, right? Because that had a -5, that had a +5. They're additive inverses, right? They added to 0, and that was great. So this was sort of an easy question for that reason. But what if we wanted to go back to the original question and say, let's do the same process one more time, but this time I want to solve for y. I want to be able to figure out what the y is, not the x. I want to do something so that when I add them together, when I do this process, the x's will cancel off, not the y's. So if the x's are going to cancel off, they have to add up to 0. They have to be additive inverses. They have to be the same numerical value but like opposite signs, right? The same absolute value with opposite signs, the same number that with opposite signs that adds to 0. So if we look at these kinds of things here, well, they'll add up to 7 right now. That's not good. We don't want them to add up to 7. We want them to add up to 0. So what we could do is use the other idea of coming up with an equivalent equation for both of these, and getting to a point where the new equation is going to have the x's cancel off. Does that make sense? Sort of? Kind of? Okay. I don't want to erase this. Let's put it over here. Okay, so we're going to have 4x minus 5y equals to 3. 3x plus 5y equals to 11. Here's my system. I've already done all this work and I've solved for x. Now I want to repeat the process, start over again from scratch, and now solve for y. But before I do that, I got to rewrite each one of these equations, and my goal is to rewrite them into a new system of equations where this is equivalent to something, this is equivalent to something, so that it's a different system of equations that's equivalent to this system of equations. And my goal is for the x's to be additive inverses. So we look at the 4 and the 3, we got to think of a common multiple. When they're small numbers like this, especially if one is prime and the other one it doesn't have the prime of the other one. So anyway, in a case like this, 12 is the smallest one we can use, right? So I want one of them to be positive 12, the other one to be negative 12. That way they add up to 0. So this is what I'm going to do. I'm going to multiply this by, say, 3. I know that if I multiply everything in the top equation by 3, I'm going to get a new equivalent equation. That's going to be 12x minus 15y equals to 9. And then the bottom one, I'm going to multiply it by negative 4. Because if I multiply everything in the bottom equation by negative 4, I'll end up with the first term being negative 12x minus 20y equals to negative 44. So I have a new system of equations. So this is kind of like that other case where like, okay, solve this, and you said, I don't want to solve that, I want to solve this instead. They're equivalent to each other, and this has the benefit that now, when I do that process, I know that these things are just going to cancel off. So I'm going to take this top equation up here, and I'm going to say that this is 12x minus 15y equals to 9. I'm going to choose to add negative 44 to both sides. So I'm going to add negative 44 over there, and I'm going to add negative 12x minus 20y over here. right? That's what I'm doing. I'm adding negative 44. I'm adding something equal to negative 44 on the other side. So then I end up with 12x minus 15y minus 12x minus 20y equals to 9 minus 44. Good. So now the x's cancel off. And now the y's combine to give you negative 35y equals to negative 35. And now we solve for y by dividing when we get y equals to positive 1. Good? So we found the y. And we had already found the x before. Any questions? Yeah?
If that negative 44 didn't have that negative, it was just regular 44, would we still adding? Or would we subtract that?
Yeah, that's fine. So we're always adding, but we might be adding a negative, we might be adding a positive. The focus really should be on these, right? Our goal was to ultimately make sure these things cancel off. So if you make sure that they're both opposite signs, then when we add them, they cancel. The other idea, and this might confuse you, the other idea is to make them both be identical so that you take one and subtract the other, and then they cancel off. But then you have to think about distributing that minus when you subtract and all that. So there is a different way of doing it where you actually subtract instead of add. But just for the sake of being consistent while you're first getting used to it, most people just add. Just to make them opposite signs, that way when you add, they cancel off. Okay, one more thing. I did it kind of the longer way, a slightly longer way, because I'm trying to get you to see the idea, the concept. But there's a much faster notation, like a quick and dirty faster notation, that makes this whole thing really, really beautiful. So let's go back over here. We're trying to solve this guy right here. And I, went through the trouble of rewriting it over here as this, and I added 11, and I wrote it this way. But most people do it this way. 4x minus 5y equals to 3, and 3x plus 5y equals to 11. Here's our system. So instead of writing it this way and going this way, what a lot of people do is this. They just put a big plus sign there, and they add down. So bring down the equal sign. This side becomes 14. When you add these guys cancel. When you add these, you get 7x. So x equals to 14 over 7. X equals to 2. Quick and dirty and easy. Right? Which is one of the great benefits of the elimination method. It really allows you to go really quickly and get to your answer. It's not different than this. It's just, it's a slightly faster notation that really encompasses this idea over here. Good? Questions? So we get the same answer, and same thing over here. Now you still have to do this step, no matter what, of rewriting it so that they have the additive inverses, so that the x's cancel. But at this stage, 12x minus 15y equals to 9, and negative 12x minus 20y equals to negative 44. You can just do that, put a plus there. These guys cancel. These add to negative 35y. These add to negative 35. Y equals to 1. So just this part of it over here can be simplified and condensed into slightly easier, faster notation. Up to you. Whatever you like, whatever you feel comfortable with. Questions? Right? So you also got to put it all together. So our solution to the original guy is this. So our solution to the system is 2, 1. Right? And we can check it by going back to this original system over here, replacing the x and y's with 2 and 1, and making sure that things match up. Okay, so check. Is it true that 4 times 2 minus 5 times 1 equals to 3? And then the other one, is it true that 3 times 2 plus 5 times 1 equals to 11? Is that true? That's going to be 8 minus 5. Yep, that's true. This is going to be 6 plus 5. Yep, that's true. So it worked out. You can also check it by solving for y in both equations, putting it on your calculator, graphing them both, and using your calculator to find the intercept. Right? Another one. Good? Questions? Okay, so you have three ways of solving systems of equations. We can graph them, we can use the substitution method, or we can use the elimination method. I think you'll find that in some cases one is better than the other. So in many of our questions, you'll find that the elimination method is probably a little bit better. The drawback to the elimination method comes when the numbers are kind of ugly. If there's a lot of decimals, for instance, the elimination method could get kind of ugly. Also, the elimination method often leads to fractions, adding fractions, multiplying fractions, dividing by fractions. So that might be a little messy. But you know, when they are nice values, the system of eliminations works out really well. The substitution method works well when it's a simple equation, straightforward equation, especially if it's already been solved for one of the variables. And also when the numbers themselves are really ugly decimals, it's usually a little better to just work with decimals at that point than the elimination method. And then of course, the graphing method is always great if you have access to a computer, a graphing tool. Okay, so when we graph two lines, we're given the system, it's got two lines, L1, L2. When we graph both lines, only one of three things can happen. Right? So if we graph, maybe the first line looks like this, L1, and the second one looks like that, say L2, which means that there is exactly one solution. I like to call it as the ordered pair A comma B. Well, you know what, this is a bad drawing for L. It look a lot like that. So this point right there is A comma B. Okay, so that could happen. That's one possibility. We have a system of equations that has L1 and L2 in it. They ask you to solve it. The solution has exactly one ordered pair, A comma B. It's up to you to find it. The other thing that could happen is that when we graph them, one line goes like this, and the other line maybe goes like that. So L1, L2, they're parallel, and so there is no solution. That's another thing that could happen, right? And then the third thing that can happen, it's kind of a silly thing, but it happens sometimes, we'll see, is that you graph the first line, and then you go to graph the second line, and in fact it turns out, oh look, they're actually the exact same line. So they touch everywhere. There's an infinite number of solutions. So this is y and x. In this case, when there's exactly one solution, we call this a consistent system. And then in this case, there are no solutions. And we call this a dependent system. And then in the last case, they touch everywhere. There's really an infinite number of solutions, right? They're all on top of each other. Where do they touch? They touch everywhere because they're really the same line. So we say that there's an infinite number of solutions. Infinite, solutions are infinite. And this system is called dependent. So a dependent system, I'm sorry, well, made a mistake. This is no solutions, this is called an inconsistent system. Inconsistent. Guys, let me keep it down. So inconsistent. So what we do is we normally assume this is the case, that there is exactly one solution. We go about our business, we either use the graphing technique or the elimination or substitution technique and find it. But when we are working by hand by the substitution or elimination method, sometimes we begin thinking that it is this one, and then it turns out that it was a bad assumption, and we will see what happens. Okay? So for instance, consider this system. We have y equals to 1/2 x plus 1 and y equals to 1/2 x minus 2. In a system like that, what jumps out at you from both of these equations? They're parallel, right? They have the exact same slope. So it's going to be one of these cases. But you might not notice it right away. Maybe you're just kind of going through it pretty quickly. You don't notice that they have the same slope. Or maybe they trick you. Maybe they disguise one of the equations in a way that doesn't make it super clear right off the bat that you're staring at a case where the two lines are parallel. So let's come up with an equivalent system of equations that's not as obvious. So we have y equals to 1/2 x plus 1 and y equals to 1/2 x minus 2. Here's my system. Yeah, they're the same slope, therefore I know that this is going to be an inconsistent system. These are parallel, there's no solutions to this system. But let's say that instead I'm just going to move this over and write the 1 over and write it as y minus 1 equals to 1/2 x. Right? This equation is equivalent to this one, right? So these are the same. I'm going to do one more thing. I'm going to multiply both sides of the equal sign by 5. I'm just making something up so that I come up with a way of disguising this equation here. So if I multiply both sides by 5, I get 5y minus 1, minus 5 is equal to 5 over 2x. Good? That looks sufficiently ugly. But this is equivalent to this one, because all I did is multiply both sides by 5. And this is equivalent, so that third one over there is equivalent to this one. And so now, if I give you a new system, I said solve this system, y equals to 1/2 x minus 2, and that one, then it might not be immediately clear to you that both of them are parallel to each other, right? It's not that easy. Okay, you could say, well, let me solve for y and simplify, move this over, divide everything. You might notice at that point that they have the same slope. But if you didn't do that, then initially you wouldn't notice it. So when you're asked to solve this system, you would proceed under the assumption that there is a solution. And then we had to do the substitution or elimination method, and something kind of curious happens. So let's proceed like we didn't know that this was an inconsistent system. So if we're going to do that, then do you want to solve it by the substitution or the elimination method? Substitution has some benefits here because one of them has already been solved for one of the variables. So it might be nice to use substitution. All we have to do is replace that y with that. So let's use substitution. So we have 5y minus 5 equals to 5 over 2x. And I'm going to replace this y with 1/2 x minus 2 times 5 minus 5 equals to 5 over 2x. Okay, so then I'm going to distribute. I end up with 5 over 2x minus 10 minus 5 equals to 5 over 2x. And then I'm going to subtract 5 over 2x from both sides. So I get 5 over 2x, and then I'm going to subtract it from both sides. So I'll get a minus 5 over 2x. Minus 10 minus 5, that's going to be minus 15. Equals to 5 over 2x minus 5 over 2x, right? So I subtracted 5 over 2x from both sides. Or you can convert it to a decimal, right? That's 2.5, 2.5, 2.5x from both sides. And look what happens. That turns into a 0, and that turns into a 0. So all the variables disappear, and the only thing that survives is a minus 15 on this side and a 0 on that side. Okay, so this just turns into negative 15 equals 0. Got it? Good? Okay, that's how we know that our initial assumption that a solution existed was wrong. We shouldn't have guessed that. This is one of the other two cases. So, when all the variables cancel out and you're left with some number equals some other number, you're either in a case where they're parallel and it's inconsistent, something like this where both lines are going to be parallel to each other, L1, L2. Or it might be that other case where you thought they were really two different equations, but really they're the same equation. So really both lines, L1 is equal to L2. Right? So it's going to be one of these two cases. How do you know which is which? Well, once all the letters cancel out, if the resulting numbers, the equation you get with the two numbers, if that is true, if you get a true statement, you're in this case. If the result is something false, like the way it is here, then that means you're in this case. Got it? So, because this is false, because this is a false, because this is a false statement, that's how I know that I'm in this case. The two lines are parallel. Okay? And that means there's no solution. They never cross. I got a false statement. I know it's this, which is called an inconsistent system. So because this is a false statement, I know that these two lines are actually parallel, and so the system is inconsistent. The system is inconsistent. No solution, right? This has no solution. There is no point that solves both of them at the same time. They're parallel. They're never going to cross. Inconsistent, right? All those things being the same. Any questions? No? Let's look at an example of this one. Well, okay, so we started with this originally, right? And I said, well, that's too obvious. That we can tell right away that they have the same slope. So we disguised it a little, right? We moved the -1 to the other side, multiplied everything by 5 to get that one. So this is equivalent to this one, which is equivalent to this one. So how about if I make up a new question where I give you a system where it's this one and this one, right? Well, obviously they're the same equation, so that's obviously going to be one of these cases. But I just want to show you what it looks like when you try and solve a system where both equations are actually the same. So, for instance, you could be given the equation or the system. So you could be given y equals to 1/2 x plus 1, and the other one, which was 5y minus 5 equals to 5/2x. Right? So we already saw that this was equal to this, which is equal to that. So these two are equal to each other. And so if I came up with a system that just has those two, it would look like this, right? So you could be given this. This could be a question. Solve this system of equations. And initially it wouldn't be clear that they're actually the same equation, right? They're trying to trick you here. They look different, but they're really the same equation. So I know that if I graph them both, they're both going to have the same graph. There's an infinite number of solutions. Any ordered pair that's a solution to this one is a solution to this one. Now, careful there. It doesn't mean that any ordered pair is a solution. I'm not guaranteed that this is a solution. You can't just make something up and say, well, any solution. No, any solution that's a solution to one is therefore a solution to the other. It doesn't mean that every ordered pair is a solution. Just there's an infinite number of points that are solutions to both. Okay, but you don't know that initially. You go about your business to try and solve this. And do you want to use the substitution method again, or do you want to use the elimination method? Elimination, just to practice. Right, if you use substitution, we do the same thing. Maybe plug in this into there, and then work things out. Just to practice, let's use the elimination method. If I'm going to use the elimination method, what do I want to do? I want to be able to cancel out some letters. What letters should I cancel out? The x's or the y's? The y's, right? All I'd have to do is distribute a, close, not 5. I need it to be -5 right there, so I need to distribute a -5. Good. So, interestingly, okay, so then I'm going to multiply by -5 in this top equation, so I'll get -5y equals to -5/2x minus 5. And then in the bottom equation, I end up with what's that negative? 5y minus 5y minus 5 equals to 5/2x. Oh, right? And then when we do the thing where we add, these guys cancel. The only thing that survives is a -5. These guys cancel. The only thing that survives is a -5. So this is one of those cases where all the letters canceled. I was just focusing on the y, but it turns out that both canceled. So all the variables disappeared, and I'm left with just an equal statement of some numbers. Some number equals to another number. And in this case, it's true. In the previous one, we had a false statement. Here we have a true statement. That's how we know that this system is dependent. Okay? So that's how we know we're in the case where both equations are actually the same thing, and the system is dependent. Right? So the solution to this, or the answer to this, is the system is dependent. Good? Questions? No? 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 Oh. So let's take a look at this one now. 1/3 x plus 5/3 equals to negative 3x minus 5. Solve this equation. Now we have a couple of ways to solve this. This one isn't too bad really. We could move the x's all on one side, move the constants all over to the other side. So we can use algebra to solve this. But rather than solving it in that manner, we want to take advantage of a little trick we learned that we're going to learn for using a graphing display to solve this. Okay, so the original question is 1/3 x plus 5/3 equals to negative 3x minus 5. Okay. So what we're going to do is we're going to think about rewriting this as a system of equations. So we're going to think of that as being a equation and being that as another equation. Maybe 1, 2. So y sub 1, say, is equal to 1/3 x plus 5/3. And y sub 2 is then equal to negative 3x minus 5. So think about this system of equations. If I graph all of these, I can use my calculator and graph all of these. I can use my calculator and graph all of these. And I will get something that's similar to this. Right? Or in fact, it might just be given. So here is an example of a graph that's given. Notice that the blue one, the blue one is 1/3 x plus 5. That's this one. And the red one is, well, not the red one, the green one is this one. Y equals to negative 3x minus 5. Okay? So even though they look like solid lines, sometimes it's useful to think about them as an infinite number of ordered pairs. There's so many of them that it almost looks like a solid line. But if we zoomed in, we would see a bunch of infinite ordered pairs, where every ordered pair is a solution to the equation here, right? It makes it a true statement. So for instance, if we look at the blue line, I could see that negative 5, 0 is where it crosses the x-axis. So on the blue one, which was this one, negative 3x minus 5, y equals to that. On this one, I know that negative 5, 0 is a solution by looking at my graph. I know that's a point on the blue line. So that must mean that 0 equals to negative 3 times, wait. What's happening here? What did I do? Blue is a different equation. You guys didn't stop me. Blue is 1/3 x plus 5/3. Good. Okay, so now the input value is negative 5. So 1/3 and then negative 5 plus 5/3. Yep, that's true, right? The left-hand side does equal the right-hand side. I inputted this for the x and this for the y, and I got a true statement. Looking at the red one, looks like the point 3, 2 on the red. Right, this one was for the blue. On the red one, I can tell that 3, 2 is a point on the red line. And the red line has the equation y equals to x minus 1. And yeah, that's true. 2 is the answer when 3 minus 1 is inputted. Right? So I just looked at a couple convenient whole number values, but there's an infinite number of decimal values that would also make it a true statement. Okay, so going back to this thing, I can tell that this one was the blue line and this one is the green line. So one point that's on both of them, the solution to the system, happens to be the point -2, comma 1, right? That's a solution to both of them. That's where they cross. It's the solution to the system. So from my picture over there, I can tell that the solution to this system, is the point -2, comma 1. So because it's a solution to the system, it means it solves both at the same time. It means that it's on the blue line. It also means it's on the green line at the same time. It means it's a solution pair for each of these. So from this top equation, I know that it must be true that 1 is equal to 1/3 times -2 plus 5/3. And I also know the bottom equation is also true. 1 must be equal to -3 times -2 plus, minus 5. That'll be 6 minus 5 is 1, true. And then up here I'll get a -2/3, which is 3/3, which is going to be 1. Yep, that's also true. Got it? Okay, so next what I want to do is notice that they both equal 1. Obviously, they both have the same output of 1. So I can set them equal to each other. So that must mean that 1/3 times -2 plus 5/3 is equal to -3 times -2 minus 5. Good? All I did is I set them equal to each other. This is equal to 1, this is equal to 1, therefore they must be equal to each other. Almost there. Now the next thing I'm going to do is I'm going to compare this to the original question we were dealing with. Right? The original question said, solve this up here. Figure out the x value that makes this a true statement. So I have to figure out what number goes in there to make this a true statement. And look, it's right here. Isn't that what that is? If x is -2, I solve that. So that's the trick with these. If you have an equation, you could to solve it, what you could do is set one side to be a function, the other side to be another function, graph both functions, and then the intercept point, the x-coordinate of the intercept point, will be the solution to the original question. Okay? So in this case, maybe it's a whole lot of work for something you could have probably done pretty easily. But as we see in the next couple of chapters, these equations are going to get really ugly, really, really nasty. And so if you face in the next couple of chapters something like this, something like log of square root of x minus 1 is equal to e to the x to the e to the x, something really nasty, like what is that? E to the x, e to the x? What? How do you solve that? Well, rather than trying to figure it out and, by hand and calculating it, we can use this little trick. We can use this function, set that as a y sub 1, set that as a y sub 2, put them in your calculator, graph them, the intersection will give you the answer, the x-coordinate of the intersection. And, well, maybe they don't even cross, right? We can tell that from the picture as well. If I graph them both and they never cross, they never intersect, then I know that they don't have a solution. Right? Or maybe they cross at lots of places, so maybe there's lots of solutions to this. Got it? Good, good, good.